Okay. All right, guys. So last time we learned about the natural log and its inverse, the exponential function e to the x. Today we learn about the common logarithm and its inverse 10 to the x. So first thing we want to show is that these functions are inverses of each other by making the xy chart and then by graphing them. So let's go ahead and make the XY chart for 10 to the X. So I'm going to type this in Desmos. Y equals 10 raised to the X. Okay. And we're going to type in those numbers exactly. So -3, -2, -1, and then 0, 1, 2. Okay. And here at -3, 0.001, and -2, 0.01, -1, we're at 0.1, and then 1, 10, 100. Okay, now in the same instance, since we're already stating that they're inverses of each other, all we have to do to fill out the numbers for the log function is take whatever we found for 10 to the x and just switch them, swap them, flip them, whatever you want to say. And this means at 0.01, you'll have -3, then -2, -1, and then 0, 1, 2. Okay, so we learned that little trick from last time. Just take your coordinates and flip them around. Of course, this only holds true if they are inverses of each other, but we will see that when we graph it. Okay, so for 10 to the x, we're not going to be able to fit 100, but we can fit 10 on there. So for 10 to the x, it's going to have -3 and 0.001. So it's going to be really close to the x-axis. And then at -2, you're not much higher. And then at -1, still not much higher. And then at 0, you're at 1. And then 1, you are at 10. So here's what the exponential function 10 to the x looks like. Almost looks like e to the x, just a little bit steeper. So this is 10 to the x. And then we'll plot the log function, log of x, and at 0.01, you're at -3. So you're going to be really close to the y-axis, so right there. And then at 0.01, you're at -2, so not much further to the right. And then at -1, at 0.1, you're at -1. So again, not much further to the right of the y-axis. And then at 1, you're at 0. And 10, you are at 1. So here's what our common log function looks like. And there it is. There's log x. Okay. And if these are true inverses of each other, then they are symmetric about the line y equals x. And we can prove that symmetry by pulling a point. This point over here is 1, 10. Reflected over, you get this point, which is 10, 1. Okay. So now we see, based on the graph and the numbers, that these two functions are definitely inverses of each other. All right. Everybody good with that so far? Can even show this on Desmos. Log of x. Look at that. And then y equals x. Here's that point, 110. And then over here is that point, 10, 1. There it is, 10, 1. Okay, awesome. And then for 3, how are the x and y coordinates of these two functions related? Give the domain and range for each function. So we'll do that above. We'll do the domain for the exponential function, which we've seen before. Remember, the domain for all exponential functions is all real numbers. The range for all exponential functions is 0 to infinity. Okay, now remember, since the x and y values switch for the inverse, the domain and range also switches for the inverse. So looking at the domain of this log function, the range of 10 to the x will become the domain of log x. So the domain will be 0 to infinity, and the range will be the domain of 10 to the x, which is all real numbers. Okay, so remember, x and y value switch, domain and range value switch, and then x and y coordinates will swap. So, or like we like to say fancy, x and y values interchange. So we can say x, y values interchange. Okay, and also, since I showed you this trick last time, how you can convert from natural log to exponential, well, we can also convert from common log to exponential and exponential back to common log. So I'll use this right here. So we are starting with 10 to the x. So here we have y equals 10 to the x. And the method is still the same. We are going from exponential to logarithm. So we are going to log. Remember that the base of the exponential function becomes the base of our logarithm. So we are going to write log base 10 of that outside number of y. Log base 10 of y will equal that exponent of x. There you go. Log base 10 of y is equal to x. Okay, now 10 is the common log base for the common logarithm. So if you ever see log base 10, you do not need to write the base in there. As you see, it's stated above. That just says log of x. So if the base is 10, you do not need to write it in. So that means that this can become just log of y equal to x. So that's how you go from exponential to common log. Now, of course, there's the other route. You can go from log, so we're going to say log base 10 of x equal to y. Now we'll go from log to exponential, and the same rules apply here. The base of the log now becomes the base of the exponential function. So this becomes 10 to the y. So you get, let me move over here a bit. So this will become 10 to the y power, and then you set it equal to whatever is inside the logarithm. So 10 to the y equals x. And there you go. That's it. And this will work for any log base. So to do one more example, let's say we have log base a of x equal to y. Then when you convert this, you will get a raised to the y set equal to x. So this works for a log with any base. And I'll put that down. Let me see. I'm going to say convert log with base a. So if your base is 5, 2, 17, 2000, this is how you would convert that. Okay. So that is another cool trick of two functions being inverses of each other. Here we can convert 10 to x to the common log, and we can convert the common log back to 10 to the x. All right. Everybody go with that? All right, I just need a calculator now. Let me move that there. Let me move that there. And then there we go. Perfect. Okay, awesome. Now we will use a calculator to evaluate these log expressions. So I have Desmos up, and we're going to type in log 1, log 8, log 800, and log 10,000. So here we go. And to type in log, it's as simple as you see it. L-O-G, look at that. Or on your calculator, you should see a log button. It's spelled L-O-G. Or on Desmos, if you go to functions, it might have log. There it is right there. You just click log and it'll do it for you. So we're going to say log of 1 and we get 0. So there's 0. And then I'm just going to change the number inside. Log of 8, we get 0.903. And then log of 800, we get 2.903. And then log of 10,000, we get 4. Okay. And it says, how are the inputs changing in problems 4 through 7 above? And how are the inputs changing? So how are these numbers inside the log changing? What are they doing?
Increasing.
Good. Inputs increasing. The inputs are getting larger. And how are the outputs changing?
Increasing.
Outputs are also increasing, but at a smaller rate, right?
Yes.
Okay. All right. C. What is the difference between how the inputs are changing versus how the outputs are changing? Oh, I just answered that, right?
Yeah.
I did. They're increasing at a smaller rate. We're just going to say rate. Rate of increase. Okay. Awesome. And when will log give an integer answer? Yeah. So when will log, get rid of that N there. When will log give an integer answer? All right, well, you have to know what an integer is. An integer is just a whole number. So when will a log give us a whole number based on your examples above? What are the only 2 whole numbers you see from 4 through 7?
0 and 4.
0 and 4. So the only time we're going to get an integer, which is a whole number, is when you are taking the log of any number that is a base of 10. 1, 10, 100, 1,000, 100,000. You will only get a whole number if it's related to a base of 10. So if I said, look, if I just increase zeros here, watch this. Log of 1 is 0. Log of 10 is 1. Log of 100 is 2. Log of 1,000 is 3. Log of 10,000 is 4, and so on and so on and so on and so on, however many zeros I want to put. So the log will only give us an integer if the input is a base of 10 or related to a base of 10. So an input is related to a base of 10. Okay. Awesome. All right. And then before we get into the next examples, I'm going to show you some cool properties for logs. We saw properties for natural logs. Now I'm going to show you cool properties for logs. All right. And we'll call these cancellation log properties. All right. Yeah. Cancellation log properties. Boom. Okay. So if you have the log of 10 to the x, well, this is going to cancel the log, and that base of 10 inside will cancel and leave you with just x. And the reason being for this is because since this is the common log, it can be written as log base 10 of 10 to the x, where this base of 10 and that base of 10 will cancel and just leave you with an x. So that's what's going on there. And again, this can work for any logarithm. Let's say we had log base a of a to the x. As long as the base of the log matches the base of the exponential function, they will cancel each other and leave you with just x. Okay, and then one more. We have 10 raised to the log of x. This will also just leave you with x. And again, the reason being is that common log has a base of 10. So here, I'll show you that background again. You can rewrite it as 10 raised to the log base 10 of x, and this base of 10 and that base of 10 match up. And then since they're the same base, they cancel each other out and leave you with x. Okay, and these were two separate, so let me separate those. Okay, and let me write the property for any log base. If you have a raised to log base a of x, it will cancel and leave you with x. There you go. There's some cancellation properties. Okay, and with that being said, let's apply what we just learned to these examples on the left. Of course, the first one doesn't represent that, but it's showing you how things cancel. So for the first one, the square root of 5 squared, that square root and the square would what?
Cancel.
Cancel and leave me with what number?
5.
5. There you go. All right. Now, number 10, log base 10 of 10 to the 9th. Well, this is going to use our first cancellation property here. So log of 10 to the 9th will leave me with what number?
9.
9. There you go. And of course, you can check it in a calculator. I'm going to type this in on Desmos. Watch. Log of 10 raised to the 9th leaves me with 9. But of course, it's a lot easier if you know the properties. You don't have to use your calculator. Okay, number 11, the same thing as 10. Log of 10 to the 7th. What does this leave me with?
7.
7. Good. And then 12 is going to use the other log property. You have 10 raised to the log of 2. Well, what am I going to be left with?
2.
2. And 13, same thing. 10 raised to the log of 5 would leave me with
5.
5. Beautiful. Okay. Everybody good with those? Okay. All right. And here we are. No room again. So let's go to my right side here. All right, we're going to start with 14 over here. We want to solve for x. So 14, we have 400 equals 10 to the x. So what we're going to do here is convert this exponential into a logarithm. So we saw how to do that on the first page. So we're going to convert 400 equals 10 to the x into a common log. So when we do that, remember that the base of the exponential becomes the base of your logarithm. So we're going to get log base 10 of the outside number of 400 and set it equal to the exponent of x. Now remember that this is log base 10, so this is the common log, and we can rewrite it as just the log of 400. And now we use our calculator and we just figure out what the log of 400 is. And for these, let's do 3 decimal places on everything. So log of 400 is 2.602 equal to x. So what this answer is telling us is that if you raise 10 to the 2.602, you're going to get a number that is close to 400. So let's check our answer out on the calculator over here. 10 raised to the 2.602 and 399.94, very close to 400. So in order to get to 400, 10 has to be raised to the 2.602. Okay, awesome. Everybody good? All right, 15. We have 50,000 equal to 50 times 10 to the x. Okay, so similar situation here. We want to solve for x, so we have to get it down from being an exponent, meaning we will convert to a logarithm. But before we convert to a logarithm, we have to get rid of this 50. And the only way to do that is to divide it off. And the reason we divide is because this 50 is connected to this 10 to the x by multiplication. So we'll just divide by 50. All right. 50,000 divided by 50 gives me 1,000. So we get 1,000 equals 10 to the x. Okay, now we need to get that exponent down. So we're going to convert to log, to the common log. So once again, this base will become the base of my logarithm. So you'll have log base 10 of the outside number of 1,000 set equal to the exponent of x. And once again, since it's log base 10, we can just rewrite it as the log of 1,000 equal to x. And let's see what log of 1,000 is. And we get 3. Okay. Not bad. All right, 16. Log of 2x equal to 0. Okay. Okay, so for 16 now, we are given a logarithm and we have to solve for x. So we have to get this x outside of the log. And the only way to do that now is to convert from log back to exponential. And since we're only dealing with the common log today, this log has a base of what?
10.
10. So we rewrite this as log base 10 of 2x. And now we are ready to convert from log to exponential. We will take this base of 10 and raise it to the 0th power. So you get 10 to the 0th, and then you set it equal to whatever's inside your log, to x. Okay. Now, what is 10 to the 0th?
0.
Anything to the 0th power is
1.
1.
1.
Okay. So you get 1 equals 2x, and then you'll divide by 2, and you'll get 1 over 2 is equal to x. So x is equal to 1/2. Okay. So now that was practicing going from log to exponential, which we'll get more practice on 17. You have log of x minus 2 equal to 1. So again, same situation here. We're going to solve for x. We need to get x out of the logarithm. So we're going to convert from log to exponential. So the first thing we want to do is rewrite this with the base of 10. Log base 10 of x minus 2 equal to 1. And now convert. 10, raise it to the first power, set it equal to whatever's inside our log, x minus 2. Okay, we've cleared the log out. We have a much easier equation to work with. Now we solve for x. 10 to the first is 10. And you get 10 equals x minus 2. Add that 2 over, and x is going to equal 12. All right. Everybody good with those ones so far?
Now, on that last one, did you
Mhm.
add 10?
What's that?
How'd you get to 12?
How did I move this 2 over?
Oh, you just add it?
That's it. Just add it to the left side.
How you know when you're going to add and when you're going to subtract?
It depends on the sign, right? So since that's negative, you have to add it to get to left. If it was positive, then you would subtract it.
Okie doke.
All right. All right. 18. Let's see. Oops. 10 to the x plus 8. So 18. 10 to the x plus 8 is equal to 20. Okay. So for this one, it's going to be just like 14 and 15. We're going to have to convert from exponential to logarithm. But the first thing we want to move over is that 8. So we will subtract 8 to the right side. And that will give us 10x equal to 12. Okay. Now you convert from exponential to logarithm. So we will get that base of 10 becomes the base of your logarithm. So you will have log base 10 of the outside number of 12 set equal to your exponent of x. And since again, this is the common log, we will just rewrite it as log 12 equal to x. And let's find out what the log of 12 is. And we get 1.079 is equal to x. Okay. 19. 7 equals negative log x. Okay. 7 equals negative log x. So this will be like 16 and 17. We need to solve for x, but right now, x is trapped inside the log. So we need to convert from log to exponential. But before we convert, we have to get rid of this negative. So all we're going to do here is divide by -1. And this will give me -7 equal to the positive log of x. But now, to save us a step, I'm going to convert this into log base 10 of x, since it's the common log. And now we will convert from log to exponential. And you'll get base 10 and raise it to the -7. So 10 to the -7 and set it equal to the inside of your log, which is x. Okay. And now 10 to the -7, that's a lot of zeros. You get 1 times 10 to the -7. So actually, we can leave our answer just like this. Unless you want to convert it to decimal, then it would be 0.01234567 equal to x. 1, 2, 3, 4, 5, 6, 7. Yep. Okay, guys. And that's how you solve logarithmic and exponential equations that have a base of 10. Any
Professor,
questions on those? What's up?
where did you get on the one we just finished? Where did you get the -1? How did you know to divide by -1? Is it because the log is negative and there's no number there, so x is understood as 1?
Exactly.
Okay.
You got it. Or if you wanted to think about it, you can add the log to the left side and subtract 7 to the right side and get the same result.
Okay.
So however you want to think about it. So yeah, you could also make this positive log x if you added it to the left equal to -7. And no matter what, we'd still get the same answer.
Thank you.
You're welcome. Good question. All right. Sweet. Now on to the application problems. All right. Everybody was good with these? Yes? Okay. All right. Sweet. All right. We'll come back to number 20. That deals with the natural log and PERT. Today, we're just working with the common log. So if we have time, we'll come back to number 20, which we should have time. I just want to stay focused on the common log and not switch it up yet. Okay. Let's see how much I can zoom on these. There we go. Maybe one more. Yeah. One more out. Okay. Sorry. All right. 21. Valium decays exponentially in the body according to the model V equals V initial. Oh, here's another E to the KT. Okay, let's stick away from those. Let's stick with common logs today. So we'll come back to 21 because that deals with E again. And I just want to stick with common logs, what we're learning. So we'll come back to 20 and 21. Okay, 22 then. The pH scale measures how acidic or basic a substance is. It ranges from 0 to 14. A pH of 7 is neutral. A pH less than 7 is acidic. And a pH greater than 7 is basic. Use the formula pH equals the negative log of hydronium. Where was it? You say H positive, H plus is hydronium content. Root beer has a hydronium ion content of 9.16 times 10 to the -4 moles per liter. What is the pH? Okay, so all we have to do here is take 9.16 times 10 to the -4 and plug it in for H. So that's how we're going to find the pH. Okay. So we'll say pH is equal to the negative log of 9.16 times 10 to the -4. All right. And for calculator wise, you're going to want to use parentheses. So we're going to say negative log parentheses of 9.16 times 10 to the negative 4. Let me make sure I just type that in right. On my other one, negative log of 9.16 times 10 to the negative 4. Yep. So we get 3.04. So is root beer basic or acidic?
Acidic.
Acidic, like all sodas, right? Acidic. Enamel ripping goodness. We should do that on what's that salt? Lucas or tahine? See how acidic those are. All right. 23. The pH of ammonia is about 11.5. What is the hydronium content? So this is giving us the pH already, and we have to solve for hydronium. So let's set up our formula first. So we have pH is equal to the negative log of H. Okay, but on this problem, they're giving us the pH of ammonia, which is 11.5. So we're going to plug that in for pH. So 11.5 is equal to negative log of H. Okay. Now our goal is to solve for H by converting from log to exponential. But what is the first thing I have to get rid of?
The negative.
The negative. So you'll divide by -1. And then we'll have negative 11.5. And since this is the common log, I'm going to rewrite it as log base 10 of H. Now we will convert from log to exponential. So base 10 raised to the negative 11.5. So base 10 to the negative 11.5 equal to whatever is inside the parentheses. So equal to our hydronium. Okay. And that's it. I mean, we want to put in scientific format because if I put 10 raised to the negative 11.5, oh, never mind. I know it's going to give me something else. So this is even better. 10 raised to negative 11.5. This gives me 3.16 times 10 to the negative 12 equal to our hydronium. I was thinking it would give me a different answer, but this is even better. So that is the hydronium content of ammonia. Okay. Everybody good with that? Okay. All right. Now, working with the same questions, determine the pH of lemon juice, which has a hydronium ion content of 3.98 times 10 to the negative 3 moles per liter. Okay. So again, using that same formula above, we have pH equals the negative log of hydronium, and they're giving us the hydronium content this time. So we just plug it into the formula. The negative log of 3.98 times 10 to the negative 3. Okay, let's see. negative log of 3.98 times 10 to the negative 3. And we get that lemon juice is 2.4. And we definitely know lemon juice is acidic. Okay. So 25, still working with the same problems. An acid reflux diet requires foods and drinks with a pH higher than 5. Would root beer or lemon juice be allowable for this diet? So root beer was 3. Lemon juice is 2.4. In order to be on this reflux diet, we need a pH higher than 5. So would root beer or lemon juice be a good choice for this?
No.
Not at all. Say no. pH levels below 5. All right. Couldn't even have lime juice. You couldn't even enjoy margaritas on this diet. That's no fun. Okay. All right. Well, everybody good with those ones so far? Okay.
Professor, I have a question.
Yes.
So that one that we just did, it talked about how the acid reflux diet requires foods and drinks that are higher than 5. So
Mhm.
since we do not have any that are higher than 5, would that mean that neither of those things would be good for the acid reflux diet then?
Exactly. So that's why I said that the pH levels of root beer and lemon juice are below 5. And in order to be on this diet, you need pH higher than 5.
Okay, cool.
So yeah, so since they're below, we don't want to give those to our to anybody on this diet.
Okay, I just wanted to make sure.
No, yeah, you got it. You're good. Okay. Awesome. Okay. 26. Using the formula R equals log of X over 0.001, where X is the seismographic reading in millimeters and R is the magnitude of the earthquake on the Richter scale, determine the magnitude of an earthquake with a seismographic reading of 23,750 millimeters. Okay, so this is telling us to plug in 23,750 in for X. So you'll have R equals the log of 23,750 over 0.001. Okay. And now you type this in, log of 23,750 over 0.001. And we would say that this scale of earthquake would be a 7 point, and we'll round to 1 decimal place. We're going to say this would be a 7.4 on the Richter scale. See, I told you guys, logs take these large inputs and puts them into a simpler format. You tell somebody on the street, like, man, that earthquake was 23,000 millimeters. They're like, what? They're like, oh, that was a 7 on the Richter scale. They're like, oh, that's bad. So it's pretty cool what logs do. And logs were cool in this situation too, where they can figure out the pH content of food. So very neat. Okay. 27. What was the seismographic reading for the earthquake off the coast of Japan in 2011, which measured a magnitude of 9.1? So now they're giving us the magnitude, and we have to find the size in millimeters of the earthquake. So using that same formula from above, here, we'll rewrite this. R equals log of X over 0.001. they're giving us the magnitude. So R is the magnitude. So they give us 9.1. And now for this problem, we're going to again have to convert from log to exponential. And I'm going to write that base in for the log. So log base 10 of x over 0.001, which means we are now ready to convert from log to exponential. So we'll say base 10 raised to the 9.1. So 10 to the 9.1 set equal to the inside of the log, x over 0.001. Okay, now we want to solve for x. And in order to solve for x, what would I multiply to the left side?
Uh, 0.001.
Good. So you would just multiply this denominator to the left side. And we get 10 to the 9.1 times 0.001 equal to x. I didn't forget a zero, did I? 1, 2, 1. Okay. And I'm going to type that in just like I wrote it. So 10 to the 9.1 times 0.001. And this earthquake that shook Japan back in the day was, what is that, 1 million? Yep, 1,258,925.4 millimeters. Look at that difference between a 7 on the Richter scale and a 9 on the Richter scale. 7 was 23,000. The 9 that shook Japan was 1,200,000 millimeters. Insane. But all we tell you guys is, hey, that was a 9. Terrible. All right. Everybody good with those two? Okay. Now we can go to those other two problems. Let's see. All right. Now we're back to PERT on both of these. So 20. As of today, the population of the United States is approximately blank million people with an estimated exponential growth of blank percent per year. Okay. Somebody get on Google and find out how many people live in America, in the United States, and somebody else find out the growth rate per year. Or ask Siri or Alexa.
331.45 million people.
331. We'll just leave it as 331.
Okay.
Why not? Yeah. And then somebody Google the growth
2.2.
rate.
2.2.
2.2% per year.
Yep.
All right.
Yep.
Cool. I like it. All right. So what is the expected population to the nearest million of the US this time in 2025? Okay. So we have to think of this as a growth problem. So is the United States growing continuously?
Yes.
Yes.
Yes, right. We're growing continuously. So we're going to have to use PERT for this. So we're going to be using PERT. Oops, that's E to the RT. There we go. Okay. So for A, what is the expected population? So let's set up our formula first. So for A, it's going to be A equals the population right now, 331 million people, times E, and this is our growth rate, 2.2%. So remember to convert it to decimal. So E to the 0.02 2 times t. Okay, where t has to be in years, of course. And if we want to know what will the expected population be in 2025, well, if this is 2021 and 2025, what will we plug in for t?
4.
4. So you'd have 331 times e to the 0.022 times 4. And let's see. 331 times e, oops, raise that to the 0.022, parentheses are important, times 4. And in 4 years, we are predicting the population to go to 361 million. Oof. That's 30 million people over 4 years. My goodness. Okay. All right then. B. When will the US population hit 500 million? All right, so when means we're looking for time. So for B, we have to take our equation. A equals 331 times e to the 0.022, and we have to solve it for time. But what we need to know first is what is the value of A? So how many zeros are in 500 million? Or what would 500 million be?
500 million?
500 million. There you go. So we're just going to say that A is 500. So remember, all of this is in the millions. So 500 million would be 500 million. And this would be 500 equals 331 times e to the 0.22t. And the first thing we're going to do is divide off that 331. And let's see, 500 over 331, and we got 1.51. So 1.51 is equal to e to the 0.022t. And now we will convert, in order to get t down, we'll convert from exponential to logarithm. But since this is a base of e, it's going to be the natural log. So when we convert, we're going to have natural log base e of the outside number of 1.51 set equal to the exponent of 0.022t. Okay, and now all we have to do to solve for t is divide by 0.022. So divide by 0.022. And this means that t, and to type that in, remember, you're just going to type in natural log of 1.51 over 0, whoops, not over 0.022. So we are expecting to hit 500 million in population in 18.7 years. Okay. 500 million in 18, almost 19 years. My goodness. Okay. Everybody good so far? Okay. So C says Why are these answers just estimates? Why are these just predicted answers? What could we possibly be missing out on?
Well, they've used the term expected and estimated, so we don't really know exactly.
True. And another thing we're not taking into consideration is that this is a growth model. We're not calculating all the people who are going to what?
Die.
Yes, die. So this is a growth model. This is why it's just an estimate. We're not counting all the people who will not be here in those 18 years.
Yeah, at the rate we're going, may not be any next year.
That's why we live our life, right?
Yeah, people don't have any regard for human life.
I hear you. All right. And then last, how would these answers above change if growth was linear instead of exponential? So this means you have to think about linear models and exponential models. So what we've seen so far when graphing exponential functions is exponential functions look like this. They have a curve. Linear models, we've graphed linear functions before. Linear functions are just a line, of course. So how would our predictions change if we went from exponential to linear? Would the growth rate be the same, or how would the growth rate be different?
One that take longer than the other.
That's it.
All
So
right.
if it was linear, the growth rate would be a lot slower, right?
Yeah.
So we'll just say linear rate is slower. Okay. Is there a Google rate of how many babies are born each day? Or is there a baby born like every hour, 2 hours? I bet you there is. Okay. Everybody good with number 20? Okay. Sweet. Okay. All right. Last one then. 21.
Professor,
What's up?
445 people are born per hour.
What? Per hour?
Yep.
My goodness, that is good to know. That's insane. Okay. So 21. Volume decays exponentially in the body according to the model V equals V initial times e to the kt, where V is the amount of volume left after initial dose of V initial with a decay rate of K over time T in hours. If 10 milligrams of volume decays to 5 milligrams in 36 hours, this is called the half-life, find the rate of decay of volume and the sign of the rate of decay. Okay, so for this problem, I'm going to rewrite the problem here. V equals V initial times E to the KT. We are going to be solving for K because we are asked to solve for the rate. Find the rate. And in order to get K down, we of course have to convert from exponential to logarithm. And in this case, it's exponential to natural log since it's the base of E. But let's go ahead and plug in the parts that it's giving us. So V is the amount of volume after an initial dose, and V initial is the initial dose. So if 10 milligrams of volume decays to 5 milligrams, this means that the initial dose was 10. and the amount after was 5. And this happened, so we have 10 milligrams and then decays to 5 milligrams. And we have time, which is in hours. So T is 36. I'm just labeling all the pieces we're given, so now we can plug in. So you get 5 equal to 10 times E to the K times 36. Okay, so our goal is to solve for K, but the first thing we want to do is get E all by itself. So what we're going to do first is divide that 10 off. And when we divide that 10 off, we are going to get, here, there's more space up here. I don't know why I didn't write it up there. You're going to get 5 over 10, which is 1/2. So we're just going to say 0.5 is equal to E to the 36K. All right. So now we are ready to convert, and that base of E becomes the base of our natural log. So this becomes natural log base E of the outside number of 0.5 equal to that exponent of 36K. Okay. Now you'll divide by 36. And when I type this in, remember you just type natural log. So natural log of 0.5 over 36. And we get that K is equal to negative 0. And let's go to 3 decimal places, negative 0.019. So there's K. But remember that K is a rate. So we want to put this rate back as a percent. So if it's negative 0.019, what would my rate of decay be?
%.
A little smaller.
Oh, it's negative.
Move it over twice and it is
Negative 1.9%.
good. Negative 1.9%. So we don't state percents as negative. So what we're going to say is that since we know that this is a rate of decay, we will say that this is 1.9%, which is our decay rate. Yes, we know the sign is negative because it's right there in our answer. K is negative. So, okay. And there it is, guys. That was common logs and the function, its inverse function, 10 to the x. Okay. Everybody go with that one. Okay, awesome. What did I send? Oh yeah, the student surveys are out. So I opened up an assignment. Let me show you guys. Because everybody's emailing now because nobody follows directions, but it's okay. So for our class, stop it. If you look in your assignments, you will see that I opened up an extra credit assignment called Snapshot of Completed Student Survey. So what you guys are going to do is take the student survey, which you're going to find on our Canvas page, which is right here in the left-hand menu, right there, student survey. Take the survey. Once you finish the survey, all you have to do is take a picture of the message saying that you have completed the survey. I don't want a picture of the survey. I just want a picture of the message saying that survey complete. Take a picture of that, upload it to this Canvas assignment, and in the comments of the Canvas assignment, and when I say comments, I mean when you upload, let me see, when you upload something, there should be an assignment, a comment box. So let's say that. You will type in the comment box, I want 5 points added to this exam. You can add it to any exam of your choice, even if the final, if you want. So upload it, and in that comment box, say, add 5 points to this exam. If you don't put anything in that comment box, I will not give you any points. If you email me, I'm going to tell you to put it in the comment box. Everything needs to be in one place. So there you go. Any questions on that? Okay. Simple, right? All right. Look at that. My inbox blew up to 10 because everybody's sending me where they want their points. But like, no, put them where I told you. Okay. All right. Well, we are done. So if you got questions, stick around. If not, see you on Wednesday, the day before Thanksgiving. Yes, we have a lot to get through on Wednesday. We're going to go through the last section of notes before your exam, and we're also going to cover the exam review. Well, I'll cover it in my normal turbo math style. So, and then Monday when we come back, that's when your exam 4 will be due, but we will have class. Since we're a day behind, we just need to get that last lesson out. And then next Wednesday will be a final exam review day. So there we go.